I welcome you back to the class of econometric methods. Myself, Dr. Imdadul Haq, an associate professor at the Department of Economics in Aligarh Muslim University. Today's lecture, we will be concentrating on a phenomenon which is called as error in variables, or we call it measurement error. See, this is a different type of error, like other than what we have studied under serial correlation or heteroscedasticity. No matter how reliable the source of data, there will always be the coefficient error in the observation used for the estimation of the fact that the most of the aggregate published series are obtained from samples, which many a times are blown up to cover the aggregate macro variables. Errors in sampling and errors in extrapolation of the samples are certain to occur, as well as in errors in observations are common. Also, in some cases, the published data refers to some variables different in content than the variables required by the economic theory. For example, the theory of consumption function. It requires the disposable income to be used as an explanatory variable, while official statistics gives figure of GDP. So, if we are using the figures of consumption function, we are bound to have an error. This is called as error of measurement. Now, this can be because of the sampling error which we just talked, like we have taken such a sample that this problem is there, or it can be when you are using proxies in place of disposable income, we are using the we are using GDP or GNP. Again, this error can occur because of the deflating procedure. Say, usually the variables included in the relationship are expressed in, say, current sales with economic theory requires quantity variables. So, in this case, it is common practice to use price indexes and deflate the value on figures. This deflating procedure may lead to errors of measurement if the index of prices is not appropriate, or if it contains some errors. So, it is or dummy variables, the use of dummy variables. Also, it is common to use these dummy variables in a function as an approximation to some explanatory variable. Dummy variables are by their nature subject to error of measurement, since they are proxies for the variables they represent. Similarly, the use of index. The index of prices, wages, etc. as explanatory variables may contain errors which are bound to be connected with the random term or with your error term. So, because of these factors, all of these, that's the sampling error, the proxies, use of proxies, the deflating procedure, the dummy variables, and the use of index, because of all these things, what can happen is that you come up with measurement error of the variables. Let us say that now we start with the thing. Let us say that we have a correct model. We have a correct model, that is ZT is equal to alpha plus beta ST plus UT, where the values, but the problem is here in the ZT and ST, they are not directly observable. The values of the independent and dependent variables, they are not observable. So, what we in place of Z, what is observed is YT. So, and Yt is what? Yt is equal to basically Zt plus an error, that is Vt. But we are not having the exact variable Zt, but we have something called as Yt, which also contains Zt along with some error. Similarly, for Xt, we want to use St, but we don't have the exact data for St, but we have the data for Xt. And this Xt is, again, it consists of St plus the error, that is Vx. Now let us look at the assumptions. Again, the assumption, this is the classical linear example assumption. Some expected value of ui is equal to 0, expected value of ui uj is equal to 0, expected value of ui uj is equal to 0, then expected value of ui square is a constant, that is sigma square u, then there is no relationship between u and v, that is the two error terms u is, there is no relationship, means you can look over here, there is no relationship between this u and this v. Similarly, there will be no relationship between this u and this vx. Then there is no relationship between z and y, there is no relationship between z and y, that is the error term, they are not, there is no relationship between s and v. Also the two error terms, means what are the two error terms? This is one error term, this is one error term. These two are also not related with each other. Then expected value of v is equal to 0. The same thing will apply for all these v's. Expected value is 0 for the v. The relationship of v at one period is not at all related, is not related to the other at v at the other period, and this v is also constant, that is sigma square, and the two error terms are not connected. The two error terms are not connected. So these are the assumptions which we have over here. Now what we are doing is, we are just, we have this was the function of yt, we don't have the data for z, but we have the data for y, and y consists of z plus an error. So we now write z in terms of z, so z is equal to yt minus, this goes over here, yt minus vy. Similarly over here, so this is sigma t, or we will call it as, or okay, this okay, at the moment this is sigma t, or we will call it as st plus vx. So here st is equal to xt minus vx. So basically the correct model zt is equal to alpha plus beta st plus ut. It can be written as, this is the model which we are assuming. It can be written as, now we have just now defined z and s, so we can, in place of z we write vt minus vy, yt minus vy, and in place of s we write xt minus vx. So now this is we can, using these information, we can write this model in this form. Now we have this model, we have just from the previous slide. So now what we do yt is equal to, we take this vt to this side, it comes over here. Next we just say that this is a composite error term, and we denote it by letter u asterisk. Next, so this becomes u asterisk. Now what we do, we are at the, we just get this final, we get this equation, yt is equal to alpha plus beta x minus v plus u. Now both bv and u are the error term. This is also error and this is also error, and this here error is multiplied by beta. So what we do, we open up this equation, we write it like this, yt is equal to alpha plus beta x minus beta v plus u, and what we see that these two error terms is the composite, we denote it by w asterisk w. So what is w? W is the composite error term consisting of u asterisk minus beta v. So now we write the final equation as y is equal to alpha plus beta x plus w. Now we want to check the characteristics, of this w. So let us see, means whether they satisfy the assumptions of OLS or not. Now expected value of w, so if we write w in the form of, So here also we add expectation, here also we add expectation. Expected value of u is equal to 0, expected value of v is equal to 0. So the expected value of w is equal to 0. Now we see, are they related with the previous or their forthcoming values? So E Wi Wj, now we write in W in terms of Ui minus Bvi, and then we write W in terms of J Ui minus Bvj. Now we have two terms, this is one and this is one. We do the cross multiplication, we get this term. That is expected ui asterisk uj asterisk minus beta vj ui asterisk minus beta vi uj asterisk plus beta square vi vj. Now ui uj 0, vj ui 0, vi uj 0, vi vj, owing to the assumptions of the model which we have started, all these terms become 0. Third, so expected value is equal to 0 and there is they are not correlated with each other also with the lagged values. Now we take the variance of Wi. Variance of Wi is nothing but expectation of u asterisk minus beta v square. Now this we can write it in the format of a minus b whole square. So a square plus b square minus 2ab. We write it like this. Now here this term u and v, we have made an assumption that there will be no relation between u and v. We discussed in the start of this lecture. So this is equal to 0. What is left? See, sigma square is a constant, beta square is a constant, and sigma v square is also a constant. So we can say that that is expected value of Wi square is a constant term. So we have seen three things. Now we go to the fourth thing. We want to check the covariance. Now when we want to check the covariance, what we do, the formula we write, what is covariance of x and w? So x minus expected value of x and w minus expected value of w. Now see, what we have seen over here, your x is nothing but xs plus v, and expected value of x is equal to expected value of s plus expected value of v. Now by assumption, expected value of v is equal to 0, and also x is one of the variables, so the true values are constant in repeated sampling, like they were in the classical assumption. We had x was constant in repeated sampling. Here s is a variable and it is also constant in repeated sampling. So what we are left with is w is equal to u asterisk minus bv, and expected value of w is equal to 0. Expected value of w is equal to 0, and this s, you can write it x in the form of this, and expected value of x we can write it like this. Your expected value was 0, so this goes away, and w we can write it in this form. Why? W is nothing but u asterisk minus beta v. So from this equation we get this equation. Now we do the cross multiplication and we can write it in this format. Because see, what we do, we write it in the format expected value of vu asterisk minus beta v square. So this we open up, we write it in terms of expected value of vu minus we write it in terms of beta e v square. Now we see expected value of v square is nothing but sigma square v, and expected value of vu is equal to 0, and this is equal to this sigma square v. So what we can write, that the covariance is equal to, because there is a beta term also, beta multiplied by sigma square v, that means it is not equal to 0. So as the covariance is not equal to 0, the least square estimated of beta is inconsistent. So that is what we were proving, that now there was a problem of consistency over here. Now so if there are errors of measurement, then the estimate of beta hat is biased. If there are errors of measurement, the estimate of beta hat, we will see it will have a downward bias. Now we go that. See, again, a biasness is a property of a small sample, while inconsistency is a property of a large sample. Now what we see, why we take the equation y is equal to, we take the equation y is equal to alpha plus beta x plus w. What we do this OLS estimation, we get this formula in deviation format. We can write it as in the normal format as summation x minus x bar multiplied by y minus y bar divided by summation x minus x bar square. Now or we can write it as summation small x xy divided by small x square. Then what we have started with, we cannot write, we couldn't observe z, so what we have taken a variable y, which is nothing but z plus y, vy. So now we take the y bar is equal to z bar plus vy bar. Similarly, we wanted to take s as our independent variable, but we couldn't observe s, so what we took x. Now x is nothing but is equal to s plus v, so we can write it as x bar is equal to s bar plus vx. Now in place of y, we write this. In place of y bar, we write this. In place of x, we write this. In place of x bar, we write these terms. So we use these four terms to insert into our normal formula for beta hat. Similarly, downstairs in the denominator we have x. In place of x we write s plus vx, and in place of x bar we write s bar plus vx bar. So these were the four terms which we have incorporated over here into the formula of beta hat. Upon opening the brackets, so what we can write, z plus vy, this becomes minus z bar minus vy, this s plus vx, and the bracket open, minus s bar minus vx. Down in the denominator also we do the same thing, s plus vx, then this comes as minus and minus vx and the whole square of it. And this is at some places sometimes this is missing, so you ignore it at the moment. So now we can write it in terms of, say, what we take these two terms together. We have z and z together, so we write z minus zy, and we take vy and vy together, so vy minus vy bar together. Here s and s together, s minus s bar. Here vx minus vx bar, so we get this term. And in in the denominator, what we write? We again take these s and s together, s and s bar. So s minus s bar multiplied by vx minus v bar, the whole square of it. Now we open the entire thing. We cross multiply each terms, because this term is multiplied with this term. It's a lot of writing over there. So this is one term and this is one term, so we cross multiply with each other. Now, so what we finally get is summation z minus z bar s minus s bar plus summation z minus z bar vx minus vx bar plus summation vy minus vy bar s minus s bar plus summation vy minus v bar vx minus vx bar. Similarly, down in the denominator we have summation. we are having this term in the format of a minus b. We are having it in the format of a minus b. So we see what we have done. It was fine over here. It was fine. Now we have it. We can write the minus sign is missing over here. So we can write it as, so this is one term, this is one term. We can write it in the formula of a square plus b square minus 2ab. The minus sign is missing over here. Please just adjust to it. So summation s minus s bar square plus summation vx minus vx bar square plus 2 summation s minus s bar vx minus vx bar. So upon incorporating these all into this, we get this equation. And see, we had assumed zx and vx are uncorrelated. It is expected the value and probability limit will be 0. No relationship between errors associated with the independent term and also no error associated with the dependent term. So the same equation is rewritten over here, and then what we have seen that, see, z minus z bar vx minus vx bar, z minus z bar vx minus vx bar, because of the assumptions it's 0. vy minus vy bar s minus y bar, vy minus vy bar and vx minus multiplied by vx bar, s minus s bar vx minus this term. So finally we are left with summation z minus z bar multiplied by s minus s bar divided by summation s minus s bar whole square plus vx minus vx bar whole square. This is what we are left with. Now we will prove that the beta hat is not only biased but also inconsistent. Suppose we increase the sample size, so plim beta hat is equal to beta, then only we can say that beta hat is a consistent estimator of B, and we can write it is consistent when plim beta probability limit of beta hat is equal to B. Now these are called the asymptotic properties. Likewise, we have asymptotic mean of beta hat when n tends to infinity will be the mean of beta. So plim beta is equal to beta is asymptotic variance is equal to 0. So consistency, this is basically an estimator is consistent if this condition is, that is the probability limit of beta hat is equal to beta, then we can say that it is consistent. We take our last value summation z minus z bar s minus s bar divided by summation s minus s bar square plus summation vx minus vx bar. We multiply both in here also, multiply and divide both the terms for this term. We multiply it by n and divide it by n. I am talking only of this term vx minus vx bar. So upon doing that, this now we can write it as vx minus vx bar. This is nothing but the variance of x. So we write it in terms of n summation sigma square ux. Now the remainder remains the same. In the remainder there is no change. So only what you have, that summation x minus x bar square divided by n, that is equal to your variance. Now you divide and multiply, means here also and here also, in both the terms, by sigma s minus s bar square. So this appears over here also and this appears over here also. So now the numerator is, it is basically, if I write it in more prominently, this is summation s minus s bar square. This is nothing but beta. And in the denominator we have, because s1 square is common over here, so we can write it in terms of 1 plus n sigma square ux divided by summation s minus s bar square. Now probability limit of beta is equal to beta divided by this whole term. Now s minus s bar square, it will be a term, it's 1, and sigma square, it must be a positive term. So meaning thereby, in no case probability limit of beta will be equal to beta. What was the condition for consistency? The condition was probability limit of beta should be equal to beta. But we are seeing that the probability limit of beta is not equal to beta, because it is beta divided by a certain constant term is there. So now Your beta is greater than probability limit of beta, so your OLS estimate, the estimate which you are getting over here, is biased and inconsistent. And as such, error in variables can only be guessed. It cannot be, it's not easy to get tested as such, but we can guess it is there or not. Now, if this problem is there, we are seeing our beta, it becomes inconsistent, it is becoming biased. What is the solution to it? So, econometricians have suggested many solutions. We discuss few of them in brief. The first one is inverse method, or we also call it inverted least squares method. This method is basically used when the independent variable has this problem and the dependent variable is fine. So, you have y is equal to alpha plus beta x minus v. Now, we can write it, we can open up the bracket, y is equal to alpha plus beta x minus beta v. We divide the entire thing by beta, so y by beta is equal to alpha by beta. Now, here beta and beta is cancelled, so what is left is plus x minus v. Now, we write this entire equation in terms of x. So, this goes to the left hand side and becomes minus alpha by beta. This minus v, it goes to the left hand side. It also goes to the left hand side, but it becomes plus. There is a mistake over here. So, it becomes plus. So, we can say that x is equal to minus alpha by beta plus y by beta plus v. Again, now what has happened, that x has become the dependent variable and y has become the independent variable. So, we can write x is equal to a plus by. What we are just writing a, this becomes a, this becomes b. So, we are writing it in terms x is equal to a plus by plus v, where a is nothing but your minus alpha by beta and b is nothing but 1, this b is nothing by 1 by beta. Now, if I use the formula for regression coefficient, it becomes, now we are writing in terms of b hat, not beta hat. So, b hat is equal to summation xy divided by now summation y square. So, meaning thereby your beta hat was equal to summation xy divided by summation x square, and b hat is equal to summation xy divided by summation y square. And similarly, your a hat is equal to x bar minus b hat y bar. So, now your b hat, as such we can say my b hat is equal to 1 by my beta hat is equal to 1 by b hat, and your alpha hat is equal to minus a hat b hat. So, as beta hat is the inverse of b hat, we name it as inverted least squares method. This is one of the method to overcome the problem of measurement error. Another one, another next method is we talk about Wahl's two-group method. See, here we arrange the observations of x and y according to the values of either in ascending or in descending. Now, let us say there are 20 observations. Then we will divide this entire 20 observations into two equal parts. And in case the observations are odd numbers, then we omit the central one and then we just divide it by. So, then we will denote the upper part by x1, y1 and the lower part of the sample by a different name x2, y2. And we will find values of y bar, values of x bar, y1 bar and the values of x1 bar, and when we will find the values of y2 bar and x2 bar. So, we divide it like this, arrange and divide the sample into upper sample and lower sample. Now, this regression line always passes through the intersection of the average values. So, this gives the impression that what is happening in the first sample will also be happening in the second sample. So, now we can write beta bar, now we can write not bar, it is beta hat. Now we can write beta hat is equal to y2 bar minus y1 bar divided by x2 bar minus x1 bar, and your alpha hat will be equal to y bar minus beta hat x bar. And the slope of this line, I am talking about this line, is nothing but this is the slope of this line, y2 bar minus y1 bar divided by x2 bar minus x1 bar. Now we take another case where we are having, we are not dividing into two, but it is basically an addition to the what we have discussed now. Now suppose here the number of observations is 33. Then we can divide it into three parts, or if the number of observations is 44, then we will omit one of the central observation. So if they are 35, we will omit 2, likewise. So we basically divide the sample into three parts. Once we have divided the sample into three parts, we will omit the middle one. So here we are dividing the observations into x1, x2, in x1, x2, x1, y1, x2, y2 and x3, y3, and we just ignore the middle one, and what we have, your beta hat, again is, sorry for the mistake, your beta hat is equal to y3 minus y1 divided by x3 minus x1. If it is two sample, we simply do x2 minus x1, y2 minus y1 divided by x2 minus x1. When it is a three sample, we divide into three parts, ignore the middle one, and your value of beta hat is equal to y3 bar minus y1 bar divided by x3 bar minus x1 bar. Next, we go to the other method that is called as weighted least squares method. Suppose our model is y is equal to alpha plus beta u. We perform two regressions. One is x on y and the other one is y on x. So we get, means we are doing that inverted, the first method which we have discussed, the inverted least square. So what is doing? We first get the value of beta hat. When we do regress y, x on y, that is summation xy, small xy divided by summation x square. Then we invert it. We have seen the inversion process. It is quickly written. We write it in terms of y by beta, then alpha by beta plus x plus u by beta. Then what we do, we write this equation in terms of x. X is equal to minus alpha by beta plus y by beta minus u by beta. Now we denote it by x. This is a, this is b, and this is u asterisk. Now, so we get, now we write the, we derive the formula for b hat. So b hat is equal to summation xy divided by summation y square. The only difference is with this and this. Here when we are doing x on y, this, the denominator is summation x square, and when we regress y on x, the denominator is summation y square. So now we have two values of beta, one with the normal one equation and the one with the inverted case. So and we have, so 1 by beta hat is also is equal to beta hat. We have seen this thing earlier also. Now we take the geometric mean, or now if I want to write this in terms, one of them is, this is b hat is equal to summation small xy divided by summation y square. We change it, we again invert it. This is the result of the inverted case. We again change it, 1 by beta hat. We know 1 by b hat is equal to beta hat. So we change it. So what was earlier, it was summation xy divided by summation y square. When we invert it, it becomes summation y square divided by summation xy. This is equal to beta hat. So now we are having two formulas of beta hat. One is this and another. So we are having two formulas. One is this is, and the other one is this. Now we take the geometric mean. This we are denoting by double hat. We are denoting it by beta double hat. So when we take the geometric mean, what we do, we under root, we write first the formula for beta hat, summation xy divided by summation x square, and the next formula beta hat, we got by inverting and then again taking the inverse. So this is summation y square divided by this one, summation y square divided by xy. So xy and xy cancelled, we are left with summation y square divided by summation x square under root n. So we divide and multiply by n, we get this finally sigma square y divided by sigma square x under root. So and now, so and your beta and your alpha double hat, similarly we have done beta double hat, then alpha double hat is equal is nothing but y bar minus beta double hat, which we have just now derived, multiplied by x bar. So basically it is based on the implicit assumption that the ratio of variances of errors is equal to the ratio of variances of the observed variables. So these were few of the methods which can be used to overcome this error in measurement. Now we have one more interesting case, that is an instrumental variable method. See, a classic example of instrumental variable is in the context of estimating the effect of education on wages while accounting for any potential endogeneity of education. Let us say we want to estimate the effect of education, that is say years of schooling, on wages or salary. However, we suspect that there might be some omitted variables or measurement error that could bias our estimates. So one potential issue is that individuals with higher ability or higher motivation might choose to obtain more education, and they may also earn higher wages for reasons unrelated to their education level. To address this issue, this is called as endogeneity in econometrics, we use instrumental variables, such as say we take a variable like proximity to college or the proximity to the university. The idea is that proximity to college or university, it affects the likelihood of obtaining higher education. Agreed. If the university is close to me, I have more chance to get educated, particularly if I am say a female candidate, there is more chance that my parents will be more happy to send their daughters to that nearby college. But the thing is, this is related to education, but this is not related to wages. Proximity to the college, you cannot say is related to wages directly. So in other words, proximity to college serves as a proxy for education that is plausibly unrelated to unobserved factors affecting wages. So this is the context of, so in this case where we are studying the relationship between education and wages, proximity to college can be used as a instrumental variable. Now, so what is, we come back to our discussion after, so this is what an instrumental variable can be. So biasness is because of the correlation between x and u. We have a problem, the independent variable and the error term are related, and this is because of this there is a problem of biasness. So what is the solution? We replace this independent variable by a different variable. And there are two conditions that should be fulfilled. First, this new variable, it should have a very high correlation with the earlier independent variable x. First condition. And the second condition, it should not be correlated with u in any case. Now, if these two conditions are satisfied, then we call it as an independent instrumental variable, we denote it by z. So we can say z is equal to, your original independent variable is x, so z is equal to x plus u. So our equation which we had was earlier, we can write it y is equal to alpha plus beta bracket z minus u plus v. So we can write it in this term, y is equal to alpha plus beta z plus plus minus beta u plus v. There is no correlation between z and v, so we can write it as, in place of what we are doing, in place of x we are writing z, in place of x we are writing z. So again, instrumental variable method is also a way out in getting rid of the problem in estimation which is happening, because if in particular cases where the independent variable is related with the error, we replace that independent or explanatory variable by a different variable, and with the two conditions being satisfied. The first is that it should be highly correlated with the existing independent variable which we are replacing, and second is that it should not be correlated with the error. So these are a few of the methods to overcome the error in variable or the measurement error. I hope this lecture is clear to you. Thank you.